Hello, this is Richard Collins, your instructor in ATM 101, Weather and Climate of Alaska at the University of Alaska Fairbanks. Welcome to Unit 3, Energy and Radiation. Today I want to highlight the fundamental ideas that we will be exploring in Unit 3. The Sun is the primary source of energy and life on our planet. This is a fact that's been appreciated by humans for a very long time and is particularly appreciated by humans living in Fairbanks in the winter. Early solar observatories were built around the world to keep track of the seasons to ensure that crops would be planted in time to mature and be harvested before the winter. Today, much of our interest in the sun is focused on harvesting solar energy directly. The map shows the distribution of solar energy around the world. This represents the amount of solar energy that would be received at the surface of the Earth over a day, and this data has been averaged over several years. What we see very clearly is there's a strong variation with latitude. As we go from the equator, 0 degrees, to the poles at 90 degrees in both hemispheres, we see that the amount of solar energy reaching the surface of the Earth falls off. If we look in longitude at a given latitude, we also see variations, and these are mainly associated with cloudiness. In cloudy regions like Southeast Asia, there is less solar radiation reaching the ground than in regions that are clear skied like the Sahara Desert of North Africa. The overarching question is, what are the flows of energy into and out of the Earth's atmosphere that maintain a habitable planet? There are several topics here, but there are three overarching topics. One is the fundamental physics of radiation. The second one is the relationship between the geometry of the Earth and the Sun and how sunlight falls on the Earth, and as the Earth moves around the Sun, how that varies and how we have seasons. And the last overarching topic is how different components of the Earth atmosphere system interact with radiation, whether they're gases, clouds, or the surface of the Earth itself. Radiation is energy that travels as electromagnetic waves. Electromagnetic waves are waves that are coupled electric waves and magnetic waves. They're the mechanism by which energy can travel in a vacuum. Waves are described by their wavelength, the distance between their crests. They can also be described by the corresponding frequency, which is inversely proportional to the wavelength. So when we have short wavelength waves, we have high frequency waves. When we have long wavelength waves, we have low frequency waves. In visible light, we have a spectrum, a range of wavelengths from 0.4 microns where we have purple light to 0.7 microns where we have red light. The short wavelength light is associated with high frequencies, the long wavelength with low frequencies. And the energy of the light is proportional to the frequency, and so the short wavelength light has higher energy than the long wavelength light, which has lower energy. There is a wide variety of electromagnetic radiation in terms of wavelengths, spanning a vast number of wavelengths. I want to highlight just two parts of the electromagnetic spectrum: ultraviolet radiation, which is higher energy radiation than visible radiation, that is on the blue-purple side of visible radiation, and infrared radiation, which is longer wavelength, lower energy radiation on the red side of the spectrum. I'd also point out that we're using radiation here as energy that radiates, not to be confused with radiation as nuclear radiation, which is particles emitted by nuclear processes that can cause cancers and other health effects. All objects emit radiation based on their temperature. Warmer objects will emit more brightly than colder objects, and they will also emit at shorter wavelengths. Here the warmest object emits in the blue more brightly than the colder object in the red. We have temperatures here are in Kelvin, 4,000 to 6,000 Kelvin. We'll come back and talk about the specifics of Kelvin in a minute. When we look at the Sun, which is at a temperature of 6,000 Kelvin, it emits with a peak wavelength of 0.5 micrometers and is quite bright at about 1750 on this scale. When we look at the Earth at 288 Kelvin, much colder, it is emitting at 10 microns, a longer wavelength, and much dimmer at a scale of 25 here. The question of Kelvin comes to the question of how we measure temperature. Kelvin is considered an absolute temperature measurement because when the temperature is 0 in Kelvin, minus 273 degrees Celsius, there is no energy emitted by the body. And it is an absolute measure based on energy, whereas 0 degrees Celsius is just the freezing point of water. The other thing I want to point out here is that we now have the idea that there's energy coming to the Earth in the visible, and there's energy leaving the Earth in the infrared, and there's a balance between the two. For the Earth to sit at a constant temperature, there must be a balance between the energy coming in and the energy coming out, that if the Earth is to stay at a constant temperature over the course of a year, then the energy in and the energy out must equal, so that at the end of the day the Earth temperature doesn't get colder or warmer on average. And we'll be seeing more of this in the next unit. The way in which the sun heats the Earth is based on the height or altitude of the sun in the sky. When the sun is directly overhead, a beam of light makes a small spot on the ground, and therefore the sunlight is quite concentrated. As the sun falls in the sky from A to B, then that spot spreads out. The energy of the sun hasn't changed, but the footprint of the sun has changed. The sunlight has become less concentrated, and therefore the ground is warmed less because the sunlight is more diluted. Therefore, as we look at latitudes on the Earth, if we go from the equator to higher latitudes, we see that at the equator the sunlight is shining directly down on the ground. At higher latitudes we're shining at a slant angle that spreads the light out on the ground, and therefore inherently there's going to be less solar energy reaching the ground per unit area at high latitudes than at low latitudes. To add insult to injury, beams of light that at high latitudes travel through a slant path through the atmosphere that's a longer path than beams of light at the equator, and so there's more chance for solar energy to be absorbed or to be lost in clouds. So this also works against the high latitudes, if you will, so that the beams of light are diminished more and then they're spread out more, and this is the major reason for why solar radiation varies with latitude on the planet. The textbook and other textbooks you've seen do a very nice job of showing pictures of the Earth moving around the sun. I just wanted to highlight some specific numbers about the seasons using Fairbanks as an example. We see that at the equinoxes, March and September, the sun is about 25 degrees above the horizon, and sunlight is spread out on the ground about 1.4 times as much as the sunlight overhead at the equator, and the path through the atmosphere is about 1.4 times longer. Not a huge difference. And midsummer in Fairbanks can get quite warm. At equinox, the sun is spread out 2.4 times as much, and the path is 2.4 times longer because the sun is lower in the sky. And then finally, at winter solstice, the sun is extremely low in the sky, and the sun is spread out 38 times as much, and the path through the atmosphere is 38 times longer. And in this instance, the sunlight becomes very weak in heating, and Fairbanks gets very cold. And this just highlights how extreme those variations are, and that the variations become most extreme when the angles become small. And that's why the winter falls away so dramatically compared to the summer in terms of temperatures at high latitudes relative to the equator. The amount of sunlight absorbed in the ground also depends on how reflective the ground is. If we have 50 units of sunlight hitting the ground and 20 of them are reflected, then only 30 of them go into the ground to heat the ground. Of particular interest to us are variations in reflectivity between, say, fresh snow, which has a reflectivity of 95%, only 5% goes into the ground, compared to, say, water, which has a reflectivity or albedo of 10%. And so albedo changes can result in significant changes in heating. If snow and ice melt, then the albedo decreases, less sunlight is reflected and more sunlight is absorbed into the ground. And we see this every spring in breakup, that as you clear the ground, the heating becomes more rapid as the dark ground absorbs heat. It can also set up a feedback mechanism where if we warm the planet, we melt the snow, and by melting the snow we allow more heat to be absorbed by the planet, and we can get a runaway effect or an amplification effect where the initial effect of warming the planet now gets amplified by an albedo change. Similarly, we see that there are high albedos associated with clouds, and so the role clouds play with albedo is also very important in the climate system. And so it's not just an issue of the sunlight landing on the Earth at some angle, it's also the properties of the Earth itself in how that light is absorbed. Looking at infrared radiation, the other side of the equation is the light emitted from the Earth. And here we see that in the wavelengths where light is being emitted from the Earth, we have methane, nitrous oxide, oxygen and ozone, carbon dioxide and water vapor all have areas where they absorb close to 1 high absorption of that radiation. And so this sets up the greenhouse effect. What happens is that if the Earth had no atmosphere, it would just cool to space. However, with an atmosphere, the Earth is cooling, letting go infrared radiation, but that infrared radiation is picked up by the neighboring atmosphere, warms the neighboring atmosphere, and the neighboring atmosphere then re-radiates that radiation back to the Earth, further heating it. It radiates some of it to space, but some of it back to the Earth. And so, if you will, the heat released from the Earth is recycled back into the Earth, making it warmer than it would be otherwise. And the current great question that we're interested in terms of greenhouse gases is the fact that concentrations of carbon dioxide are rising. Therefore, we expect there to be more energy in the atmosphere, and possibly we expect that the atmosphere should generally warm. The other gas that's important in the atmosphere in terms of its interaction with radiation is ozone. On the previous slide, we showed that there's strong absorption due to ozone in the atmosphere, and the high energy ultraviolet light that is blocked is very important because if that light came to the ground, it would disrupt biological functions. One of the things to highlight in ozone or any other gas in the atmosphere is that there is a chemical balance. Ozone molecules are in a cycle with oxygen molecules and oxygen atoms. The population of ozone overall stays relatively stable, but individual molecules and atoms are cycling through different compounds very quickly, but the overall population stays constant. That overall population is in a chemical balance. If we change other chemicals in the system, we may get a population that's smaller or larger. If we change chlorine in the atmosphere, we get a balance where there's less ozone and therefore less absorption of ultraviolet light and more ultraviolet light reaching the ground. This happens catastrophically in the ozone hole, where two things come together: the human release of chlorine into the atmosphere and the unique meteorology of Antarctica with very cold temperatures. And here's a picture of the ozone layer in Antarctica. The solid line in August is a typical ozone layer with height, with a peak at about 17 kilometers. And that's when there's low chlorine in Antarctica before sunlight returns to Antarctica. And then with the return of sunlight, we see high levels of chlorine released and immediately a balance with destruction of ozone, and you can see the ozone practically disappears. And this has been the great concern about the ozone hole and global levels of ozone, that chlorine may have diminished them. And this is why we banned CFCs as a global community to restore the ozone hole, hopefully sometime in this or the next century. Clouds are a very important part of the radiative balance. Clouds interact with radiation in two very important ways. Because they're high albedo, they reflect sunlight and they have a cooling effect during the day. Clouds are also made of water, which is a greenhouse gas, and water interacts very strongly with infrared radiation. And so on cloudy or humid nights where there's a lot of water vapor in the air, radiation from the Earth will be absorbed by the clouds and then re-radiated back to the Earth, warming the Earth. And so in general, cloudy days are cooler than clear days, while cloudy nights are warmer than clear nights. Changes in clouds and changes in albedo are part of the largest uncertainty in how we think the climate will respond to changes in greenhouse gases. If there are changes in the water vapor cycle that change the way clouds work, that could have a big effect on maybe making the planet cloudier and blocking solar radiation and maybe counteracting some of the effects of greenhouse gas warming. These remain active research areas in climate science. In terms of Alaska, we have some measurements of solar radiation and solar energy on the ground in Alaska through the seasons at several sites. Here we have Anchorage, Barrow, Fairbanks, and Annette. Annette in southeast Alaska, Anchorage south central, Fairbanks in interior, and Barrow on the Arctic North Slope. You can see that the concentration of sunlight at the ground depends on solar altitude, the length of the day, and the cloudiness. And you would expect crossing Alaska that the sun is higher in the sky as we go south and lower in the sky as we go north. The length of day is longer in Barrow in the summer than it would be in Annette. You don't see a lot of variation here, and that's partially because of variation in cloud cover. And so, for example, Barrow has longer days, but it has cloudier skies than Fairbanks in high summer. Anchorage has the sun is higher in the sky, but it's generally cloudier in the summer. The other thing just to highlight in terms of Fairbanks is that there's less clouds in March, April than there is in July, August, and therefore we actually get more sunlight in Fairbanks early in the summer than late in the summer. We're slightly skewed because of the skew in our cloud cover. So all those elements are coming together and we see them in the data from Alaska. Closing thoughts and summary. I can read the bullets here. I'm just going to reflect on them generally. All objects absorb and emit radiation, and the amount of radiation emitted by a body is related to the temperature and defines the fundamental temperature scale of Kelvin. That when we're at absolute 0 degrees Kelvin, very cold temperature, it's the lowest we can go, and at that point there is no radiation emitted by a body. Latitude is very important in how the sun heats the ground, and seasons are caused by the tilt of the Earth and more pronounced at higher latitudes. There is a balance in the atmosphere between absorption of sunlight or visible radiation and emission of heat or infrared radiation. If there was not a balance, then the Earth would keep cooling if it was emitting too much radiation, or it would keep warming if it was absorbing too much radiation all the time. But we end up in a balance in that the Earth on average stays pretty constant year to year. We'll talk about trends in climate later in the semester. Different gases in the atmosphere interact with different types of radiation. The ozone layer blocks ultraviolet radiation very effectively and is an important part of maintaining life on our planet. The absorption and re-emission of infrared radiation by greenhouse gases is very important in maintaining a warmer temperature than we otherwise might expect. That also helps life on the planet. Remember, life on our planet is tied to the fact that we have liquid water. Maintaining a range of temperatures that allow liquid water to exist is very important. And finally, as concentrations of greenhouse gases increase, we would expect the atmosphere to warm, but it doesn't guarantee the atmosphere would warm. There are other elements at play in terms of feedbacks in the system about how albedos might change if cloudiness changes. And so it is not an automatic guarantee to say that increases of greenhouse gases automatically guarantee increases in temperature, and there are also huge regional effects at play that we'll discuss later in the semester. Thank you.